Hi, Pre-Calc. We're up to Trig Day 5. Today we're going to take a look at solving some quadratic equations as it relates to what we've done with trig equations. So in each example today, we're going to solve over the interval from 0 to 2 pi. And this will be a standard in this unit is when we're solving equations, typically just getting all answers in radians. So we have to, if we're still a little uncomfortable with radians, just keep practicing at it. The more you try and force yourself into sticking with radians and not converting back and forth between degrees, the better off you'll be. But you can see our first example that we're going to solve here. 2 cos squared theta plus cos theta equals 0. And when you see this squared term here, that's what's making this quadratic. And I'll have you kind of think about comparing this to solving the equation 2x squared plus x is equal to 0. I probably won't use this approach too often where I use a dummy variable to solve the quadratic and then replace it in the end. But if it really helps you to get started, if you say let x equal cos theta, then this becomes 2x squared. And maybe it's easier for you to visualize just initially how to get started on something like this. Well, what I'm going to do is if you think over here that there's a GCF of x, coming back to the original, there's a GCF of cosine theta. So that's what you're going to do to get started in number 1. Take out the GCF of cosine theta, and you're left with 2 cos theta from the first term, plus, don't forget about plus 1 over here, right? You want to make sure if I distribute cos theta back in, we get back to the original. So once I do that initial step of factoring out cos theta, now we're up to a stage when we're in factored form, setting each of our factors equal to 0, including the cos theta that we have as our GCF that we factored out. So we're going to solve when does cos theta equal 0, and then on this side, if you wind up solving and get cos theta alone, you would subtract the 1 over and then divide by the 2. So on this side, you're going to figure out when does cos theta equal -1/2. All right, so let's go ahead and do the left side first. Cos theta equals 0 has 2 solutions. Those 2 solutions do not come from drawing triangles at all. I mean, how would you even know what quadrants to draw them in? They come from the unit circle. So whenever you have a trig function equal to 0, it's got to be a unit circle question. Now, what we have to remember is that cosine of an angle goes with the x value on the unit circle. So we're looking for when is the x value 0, which happens at the top and at the bottom of the unit circle. And remember that the answer for theta then are what are the angles that correspond with those locations. So we're going to get theta equals pi over 2. And then additionally that theta equals 3 pi over 2. Okay, those are the 2 solutions that we get on the left side of the wall here when we use the unit circle. Now on the right side, cos theta equals -1/2, we'll also get 2 solutions over here. But these are going to come from triangles in quadrants where cosine is negative. So all-star trig class would tell me that cosine's negative in quadrants 2 and 3. So you're going to draw triangles in those 2 quadrants. And then we know that the ratio for cosine is adjacent over hypotenuse. So the adjacent side, which is the side that's kind of being shared here, is the -1. 2 would go on the hypotenuse. The opposite is the radical 3, if you want to fill that in. Because if that helps you to get this reference angle right here, that's what we really need to know. And the reference angle across from a radical 3, I'm going to just do it in radians. We got to kind of try and stick with radians as much as possible here. The reference is pi over 3, okay, which is 60 degrees. Okay, but 60 degrees is pi over 3. How do I get my 2 answers then? Because pi over 3 is a quadrant 1 angle. So remember that if you're dealing with halfway around the circle is pi, then with the denominator of 3, this is really 3 pi over 3 if we go halfway around. So in quadrant 2, I'm going to do the full half circle, 3 pi over 3 minus the reference of pi over 3. So in quadrant 2, we get 2 pi over 3 as an answer. And 3, you would take the full half circle, which is 3 pi over 3, and add on that reference of pi over 3, which would get you to 4 pi over 3. So the other 2 solutions are 2 pi over 3 and 4 pi over 3 respectively there. And although it's not a requirement, when I write my solutions in the end, I am going to list them in order, and I'll explain why I think that's useful. So the smallest angle that I get as a solution is actually the pi over 2 from over here. because that's right on the border of quadrants 1 and 2. Then I get my quadrant 2 answer of 2 pi over 3. In quadrant 3, we get 4 pi over 3. And 3 pi over 2 is the largest of your solutions because it's right on the border of quadrant 3 and quadrant 4. So those are the 4 solutions to when this equation equals 0. And the reason why I think that's useful to have them in order is, what if I said, all right, well, now answer the question, when is 2 cos squared theta plus cos theta greater than 0? And similarly, we can do the same thing and answer, when is it less than 0? Well, we're going to look at this on the calculator just like we did on day 4. So we're going to type this into y equals. Make sure, again, you're still in radian mode if at some point you had switched back over to degree. But we're going to do 2 and then cosine x. Remember that this notation right here, cos x squared, is the same thing as we write cos squared. Plus cosine x. And I'm just going to double check my window in case I had changed that recently. It still looks like it's 0 to 2 pi, which is good because that's the interval that I'm solving over. When I think about the range of values that we should get for cos, -3 to 3, I'll kind of make that y max of 3 there. That should be sufficient. So if I go ahead and hit graph, hopefully I'll find that we get 4 solutions. And it's a little tough to tell, but you do get 1, 2 right here, and then 3, 4 that are pretty close by. Okay, so we get the solution that looks like some nice symmetry going on here. So the graph winds up looking something like, where can I squeeze the graph in? I'll do it over here. Okay, the graph looks like this, like that. Okay, so it's important, like I said, to list these solutions in order, because now when I go ahead and list where is it greater than 0, it's nice to know that this is pi over 2 and this is 2 pi over 3. Okay, so let's answer those 2 questions then. Where are we greater than 0? Well, we're greater than 0 from 0 to the first solution, which is at pi over 2. By the way, you can include 0. Okay, that would be okay to include. So from 0 to pi over 2, we're greater than 0. Then we're greater than 0 in between here from 2 pi over 3 to 4 pi over 3. All right, that's these 2 solutions in between. And then from the last solution, which is 3 pi over 2, up until 2 pi. Oops, sorry, I can barely squeeze that in. Okay, 2 pi is not going to be included there because 2 pi is really never included in those intervals when we write the solution. But 0 definitely makes this a true statement, so I want to make sure that I include 0 there. Okay, so that's the greater than 0 part. What about the less than 0? The less than 0 occurs really in between both solution points there. So it's less than 0 from pi over 2 to 2 pi over 3. And then also from 4 pi over 3 to 3 pi over 2. Okay. Now, I haven't really done this yet, but just to really double check that we got the correct solutions, I'm just going to check one of them here. If you calculate this first 0, let's say second trace, I'm going to calculate one of the zeros. I'll do the one on the far left side, which we know should be pi over 2. Hit enter when you're to the left of the 0, scroll to the right of it, hit enter again, and then enter for the guess. And it doesn't tell you pi over 2. It tells you 1.5707 ... Now remember that number, because if I come back to the home screen and I type in pi divided by 2, that's that 1.5707 number. So I think beyond just saying, okay, we have 4 answers, are they the correct answers? You can check on the home screen that the decimal version of your radian answers matches the decimals that you're seeing on the graph right here. Okay. All right, so this is a little bit of a taste of, now we're going to expect to see a bunch of solutions. We've seen up to 4 in the other lesson, but now we have to do a little bit of maybe factoring to kind of get going in some of these questions. So for number 2, let's take a look at sine squared plus sine x minus 2 equals 0. Now, if it really helps you to get started, think of this as being the same thing as x squared plus x minus 2 equals 0. So it's very similar, right? If you use the dummy variable, let x equal sine x, which I don't love the same variable, but you guys get the idea. Okay, it becomes a quadratic equation. So if we think about how do we factor a trinomial using that add multiply method, right? Adds to 1, multiplies to -2. whatever those factors are with x's, now it's going to be the same thing, but with sine x's, okay? So sine x times sine x is the only thing that would get me back to sine squared. I want to figure out what multiplies to -2 but adds to 1 in the middle. And that's going to wind up being a +2 and a -1. Okay, so once I get this factored, then I set each side equal to 0. On this side, we're going to get sine x equals -2. And then on this side, we get sine x equals 1. So I'm going to ask myself, where is sine negative? Well, sine is negative in all-star trig class quadrants 3 and 4. Remember, sine is opposite over hypotenuse. So the opposite would be 2 and the hypotenuse would be 1. And as soon as you make that label, although this ratio looks pretty familiar to us of like 2 over 1 and 1 over 2, look at this triangle right now. The hypotenuse is 1 and the opposite side is 2. That's impossible to have happen. So what we know about this left side, without even probably drawing the picture, if you have a ratio for sine that exceeds the range of -1 to +1, those are the only values that could possibly work. There is no solution here. You can't do sine x equals -2. It's impossible. So when you have sine x equals something, it has to be somewhere on the interval from -1 to 1. Otherwise, you're not going to get any answers. So to that extent, it makes actually this side pretty easy to do. Since sine x equals 1 over here, you will get some answers, but those answers don't come from triangles. Sine x equals 1 is definitely a unit circle question, so draw the unit circle. If sine goes with y, we're thinking about where is the y value on the unit circle. 1, and it happens to be right up here at the point 0, 1. Okay? So the only solution you're going to get to this quadratic equation, here we got 4 answers, but this only has one singular answer. It's when x equals pi over 2 in radians, and that's it. I'll double check it real quick just to make sure that we only get one solution by typing in the equation, sine x quantity squared. And then what did I have? Plus sine x in the middle and -2. And if I hit graph, I should only see that we cross at or touch, I guess, once at pi over 2. And then the rest of the way to 2 pi, we don't have any other points of intersection with the x-axis. Okay? So quick graphical check there. I won't do the inequalities for this one, but we are going to do one more. All right, last one for today is let's solve the equation. Tan squared x plus tan x minus 2 equals 0. And if you're writing this down and you're like, gosh, why does that look so familiar? I feel like we just did this. Well, we kind of did. We just did sine squared plus sine minus 2. What about tan squared plus tan minus 2? It's going to have a similar feel, but the solutions are going to look vastly different when you put the tan function in here instead of the sine function. The factoring part looks the same. It's going to be tan x plus 2 and then tan x minus 1. So that part looks very much the same. I'm going to then from there separate the factors and get tan x equals -2 and tan x equals +1. But once we get down to this stage, that's pretty much where the similarities end. Because I'll tell you right now, this one doesn't have one solution. This one has 4 solutions. There are 2 answers to when tan x would equal -2. Because remember, for tan, we're looking at opposite over adjacent. The opposite and then the adjacent could be 2 and 1. But we have issues with sine and cos when those depend on the hypotenuse in the denominator. The hypotenuse can never be less than the opposite or the adjacent side. Okay, so where is tan negative? All-star trig class would tell me tan is negative in quadrant 2 and then in quadrant 4. So you're going to label the opposite side as 2, the adjacent as 1. Opposite of 2, adjacent of 1. Okay, so there's the labels. Now, it's really tempting to think that this is a special triangle because we have a 2 and a 1, and we think, oh, yeah, the missing side's radical 3. But that's only when 2 is on the hypotenuse. Is this a special triangle? So here's the deal. If you want to find the solutions in quadrants 2 and quadrant 3 here, you need the calculator to do it. This is not a special reference angle. So I don't know what this is right now. To get the reference angle, here's what we're going to type into the calculator. you're going to type in tan inverse of positive 2, which we're used to from the beginning part of our unit on trig here. We found not so nice looking reference angles earlier on in the trig unit. But let's see what this comes out to be if we do tan inverse of 2. Remember, the negative just helped me to figure out the quadrants. It's super important that we only type in tan inverse of a positive amount. So if I hit second tan of 2 only, and we're in radians, tan inverse of 2 is 1.107. I know that's not a nice looking reference angle, but this is just the reference, which is 1.107 ... Okay. From there, how do I get my answers? Well, in quadrant 2, what I'm going to do is well, I shouldn't say full half circle, but half circle is pi. Pi minus that little reference is how we get the quadrant 2 answer. So pi minus this reference is 2.03. We'll go to the hundredths place. Okay. In quadrant 4, how would I get my answer? Well, in quadrant 4, if I go full circle, that's 2 pi. But then I have to subtract out that reference angle to get the quadrant 4 angle. So this one's 2 pi minus the reference. Let's go ahead and do that. 2 pi minus, go back and get that reference angle from the beginning, 1.107. That's 5.18 to the hundredths place. Hundredths place is, I would say, typically a rounding standard. I know this part of the problem is actually pretty challenging, okay? But these are the two answers to when tan x equals -2. Now, I know I rounded that answer, but if I was to do tan of 2.03 right now, you're going to get an answer that's real close to -2. I mean, I know it's not exact, but that's how we can almost double check. Like, does that even make sense? Yes, it does. Tan x equals 1. This side, I think, will be a little bit easier. We're looking for where tan is positive, which is in quadrant 1 and 3. Tan is opposite over adjacent, so the opposite and adjacent both get 1s. But this winds up being a special triangle. The hypotenuse is radical 2 here, so the reference angle, when you have a special triangle like this, is pi over 4. And remember that halfway would be 4 pi over 4. So to finish out the quadrant 3 angle, you would do 4 pi over 4 plus the pi over 4 into quadrant 3 for an angle of 5 pi over 4. So we have 4 answers altogether. Let's see if we can write them in order. Solutions. The first solution is in quadrant 1. That's the pi over 4 right there. Pi over 4 is an answer. Then we had a quadrant 2 answer from this side. It's 2.03. The quadrant 3 answer is a nice exact 5 pi over 4. And the quadrant 4 answer is 5.18. It looks really weird to have a combination of nice looking radian angles and not so nice looking radian angles. But I promise it will actually just become the new normal in this unit. Okay. All right, let's just do one of the inequalities. Let's solve when is tan squared plus tan x minus 2 greater than 0. Okay. Now keep in mind, these are my solutions in the order. I'm going to see where it hits the x-axis in those places. So we're going to do tan x squared and then plus tan x minus 2. Let's hit graph, see what happens. All right, we get our 4 answers. Oh, but yeah, remember that tan has these weird asymptotes, right? So when I think about what the graph looks like, which is this piece, asymptote, we get this in the middle. We've seen graphs like this before. That's what the graph looks like from 0 to 2 pi. Here are my 4 solutions. If I want to figure out where this is greater than 0, here we go. Ready? Well, the graph is greater than 0 from my first solution, but I have to stop at that asymptote. So it's from pi over 4 up to the asymptote at pi over 2. And the asymptotes for tan are, for right now, always pi over 2 and 3 pi over 2. All right. And then we pick up again at pi over 2 up until the next solution, which is at 2.03. That looks weird, but go with it. Then we have to jump across here. We're also positive from the next solution, 5 pi over 4, up until the asymptote at 3 pi over 2. And then I got to even come down to the next line here. Then from 3 pi over 2 up until the last solution, which was 5.18. And that's the solution to when this is greater than 0, all 4 of those parts. I know that's kind of a lot to put together. I promise we're going to do more practice with this in this unit, but get used to it. You're going to see some not nice angles. If you can't get a good reference angle here, sometimes even mixed with some really nice angles and radians that we can generate in terms of pi. Okay, so more to come with solving some quadratics. We may even throw in some quadratic formula in the future. I know you're excited. All right, have a good day.